Okay, let's dive into this. In this explainer on distributed systems, we're tackling one of the most fundamental and honestly kind of the most fascinating challenges in modern computing. When we write software on just a single computer, it's so tempting to think of our machines as these mathematically perfect, totally deterministic boxes. We write a line of code, press run, and expect it to execute flawlessly every single time. But to really grasp how large-scale systems work, we have to completely shatter that illusion right out of the gate, because computers go to massive lengths to hide the chaotic physical reality they actually operate in. Underneath all those clean digital abstractions, we're dealing with physical components sitting in hot, incredibly noisy data center warehouses. Things are wearing down, breaking apart, and misbehaving all the time. We are constantly fighting entropy, the inevitable decline of any physical system into total disorder. And when we graduate to distributed systems where thousands of machines are trying to talk over unreliable network cables, well, we can't ignore that chaos anymore. We have to confront it head-on.
I absolutely love this quote from A.A. Milne. They're funny things, accidents. You never have them till you're having them. In software development, it is dangerously easy to put all of our energy into what we call the happy path. You know, that pristine, idealized scenario in a developer's head where the network is blazing fast, the hard disks are perfectly healthy, and users always type exactly what they're supposed to. But the second you move that software from a laptop into a production environment, you are in a totally different world. Any experienced systems operator will tell you about the sheer chaos they face every day. They know from some very hard-earned experience that anything that can go wrong eventually will. Anticipating every possible fault is an unbelievably difficult challenge. But if we ignore them and just build for that happy path, we aren't really engineering at all. We're just waiting around for an accident.
So that brings us to a really fundamental question that shapes pretty much everything we do in systems architecture. What does it actually mean to be reliable? It's a buzzword we throw around constantly in the tech industry, but defining it formally is notoriously tricky. Just think about what we demand from our apps today. We expect them to work instantly, to gracefully handle us clicking the totally wrong buttons, to keep out bad actors, and to never, ever lose our data. Trying to wrap all those massive expectations into a single operational philosophy is a monumental task. How do we build digital ecosystems that acknowledge the chaotic reality of accidents, but somehow just keep working?
Well, here's our formal definition from the source material. Reliability simply means continuing to work correctly even when things go wrong. I want you to pay close attention to that second half. Notice what it doesn't say. It's not about preventing things from going wrong. In a massive distributed environment, preventing all errors is basically impossible. True reliability is entirely about surviving those errors. It's kind of like a multi-engine commercial airplane. The engineers don't just sit around hoping an engine never fails. They meticulously design the plane so that if one completely blows out mid-flight, the plane doesn't drop out of the sky, right? It just keeps flying, gets you to your destination, and handles the crisis in the background. Our software architecture demands that exact same philosophy.
So, the crucial point we really need to nail down here is the difference between a fault and a failure. In casual conversation, sure, they sound like the exact same thing, but in systems engineering, they are completely different levels of consequence. Let's break it down. A fault is when one specific, localized component stops working. Imagine a massive server rack, and one single hard drive just starts grinding and dies. That's a fault. The system as a whole shouldn't really care. A failure, on the other hand, is an outage. It's when the whole system stops providing its service to the user. Like, if that one dead hard drive happened to hold the only copy of your customer authentication database and suddenly thousands of people are locked out, that is a failure. Our ultimate goal is to isolate and tolerate faults so they get absorbed before they can cascade into a total system failure.
And that distinction leads us right into something system architects spend their whole careers hunting down: the single point of failure, or SPUF. If your architecture simply cannot tolerate a specific part failing, that part is a single point of failure. Going back to our database example, if you only have one primary node and 0 backups ready to take over, that node is a massive vulnerability. The absolute second a fault happens there, boom, it escalates into a catastrophic system failure. Think of it like a giant multi-lane highway that forces all traffic through one single toll booth. One flat tire at that booth, and miles of traffic grind to a dead halt. To build genuinely reliable systems, engineers have to obsessively audit their setups, find these bottlenecks, and completely eliminate them.
Hardware faults, the physical reality. Let's look at what actually goes wrong.
So let's start with the foundational stuff, hardware. Physical degradation is usually the first thing that comes to mind with outages. And get this, it turns out about 1 in 1,000 machines in a given fleet has a CPU core that occasionally just computes the wrong mathematical result. Let that scale sink in for a second.
In a data center with tens of thousands of servers, you are guaranteed to have defective processors, mostly from microscopic manufacturing flaws. Sometimes this bad math just crashes your program, and ironically, that's the best-case scenario. A hard crash is visible, you can replace the machine, but other times it operates normally and silently returns the wrong result, quietly poisoning your database. That is literally a nightmare scenario for maintaining system integrity. And the chaos doesn't stop at the CPU. Over 1% of all machines encounter an uncorrectable memory error every single year. Sometimes it's a physical defect in the silicon, but incredibly, this can also be caused by cosmic rays. Subatomic particles traveling across the universe can strike the physical memory chips in your server with just enough energy to literally flip a bit from a 0 to a 1. It's wild, right? We actually have to account for deep space physics when building web apps. And zooming out from the microscopic stuff, we have macro-level physical disasters. Earthquakes, floods, power outages, fiber optic cables getting sliced by construction crews, or even a solar storm inducing rogue currents in the power grid. They're rare, but they show the massive scale of hardware faults we have to be ready for.
So how do we actually fight this barrage of hardware faults? Well, historically, the answer was just redundancy. Just buy extra stuff. We use RAID configurations to seamlessly spread identical data across multiple physical disks. We installed dual power supplies plugged into totally different power grids. But as systems grew to a global scale, we had to shift our thinking. Instead of just buying more redundant hardware, we now build fault tolerance directly into the software itself. By designing apps to survive the sudden loss of entire physical nodes, we leverage cloud availability zones to survive a whole data center going offline. This software-first approach also gives us a superpower: rolling upgrades. We can intentionally turn off one node at a time to apply security patches, and the software effortlessly routes traffic elsewhere. The user never even notices.
Software faults, systemic, and correlated. Moving up the stack.
Securing the physical hardware is really only half the battle. Software faults are a completely different beast, and they require a totally different mindset. Because unlike hardware faults, which are usually independent, one server losing a hard drive doesn't mean the server next to it will lose one. Software faults share a truly terrifying trait. They are highly correlated. Since modern distributed systems consist of thousands of nodes all running the exact same code, a logic bug isn't an isolated issue. It means you have thousands of identical ticking time bombs waiting for the exact same trigger. Because they're systematic, a single software fault can take down dozens, hundreds, or all of your nodes at the exact same millisecond.
The history of software engineering is full of these crazy, almost cinematic correlated nightmares. Take June 30, 2012. A perfectly normal leap second was added to global clocks. But that tiny adjustment triggered a hidden bug in the Linux kernel, which caused massive numbers of Java applications globally to just freeze up. Major internet services literally vanished from the web at the exact same moment, all because a clock ticked one extra second. Or how about a famous firmware bug that caused a specific SSD model to completely lock up after exactly 32,768 hours of operation? Since companies buy drives in bulk and turn them on at the same time, massive arrays of drives just turn into unrecoverable bricks simultaneously. Add in runaway processes that eat all a machine's memory, or cascading overload failures where one slow service dumps its traffic onto another until everything collapses like dominoes. These bugs just lie perfectly dormant, waiting for the worst possible time to strike. Because these systemic software faults are so deeply ingrained, there is absolutely no magic bullet here. Handling them requires some serious defense and depth engineering. First, we have to relentlessly question the assumptions our code makes. Second, we rely heavily on strict process isolation. If a process acts up, isolation quarantines it so the bug doesn't consume the whole host machine. Third, we have to design systems to safely and quickly crash and restart. Honestly, it's almost always better to cleanly kill a failing process and start fresh than to let it hang indefinitely. And crucially, we have to meticulously measure and monitor everything in production. Good monitoring is our early warning radar, letting us spot subtle issues before they trigger a catastrophic cascade.
Humans and reliability, the socio-technical system.
Let's move on to our final and, frankly, most unpredictable fault category of all: humans. At the end of the day, we are the ones designing, building, and running these complex architectures. And unlike machines, we adapt, we get creative, we get tired, and yeah, we make mistakes. When researchers look at massive outages at large internet services, a really fascinating picture emerges. Those physical hardware faults we talked about earlier, they only play a primary role in roughly 10 to 25% of major outages. The single leading cause of massive system downtime is actually human configuration changes. The operators trying to keep the system running are, statistically, the biggest threat to its uptime. And it isn't because they're careless, It's because modern microservices are so incredibly complex that predicting what one operational change will do is just monumentally difficult.
Now, when an outage happens because of a bad config change, it is so tempting to just point the finger. Oh, Bob typed the wrong command, so it's Bob's fault. But our source text emphatically warns against this. Blame culture fixes absolutely nothing. The core philosophy here is that human error is a symptom of a problem with the socio-technical system. Professionals are generally trying their absolute best. When a devastating mistake happens, it's almost always because the system set them up for failure. Think about a tiny, vaguely worded confirmation prompt that, if you click it too fast, permanently deletes a production database. That is poor tooling. It makes doing the catastrophically wrong thing way too easy. Blaming the operator ignores the systemic flaw that allowed that button to be so dangerous in the first place.
So instead of pointing fingers, organizations need to aggressively build technical safety nets. This means investing heavily in automated testing so changes can be simulated safely. It means building robust rollback mechanisms so when a bad update inevitably goes live, the system can revert to a healthy state in seconds. And it means using gradual rollouts. You don't push a risky update to millions of users instantly. You push it to 1%, watch the monitoring, then 10%, then 50%. You intentionally minimize the blast radius. But there's a harsh business reality here. These safety measures require massive time, effort, and money. Companies often face huge pressure to push new, revenue-generating features rather than investing in invisible resilience. So when a preventable human mistake causes an outage, it's often a reflection of organizational priorities rather than simple operator error.
Embracing fault tolerance, pulling it all together.
So we've looked at physical hardware dying, highly correlated ticking time bombs in our software, and the unpredictable nature of human error. To truly embrace fault tolerance, we have to look at a radical operational philosophy: chaos engineering. This is where we bring all these lessons together. If the core problem is that faults are inevitable, the solution isn't to hide from them. The motto of chaos engineering is basically, if it hurts, do it more often. If we want to be undeniably certain our system can handle a database node dying, we shouldn't cross our fingers and wait for it to happen at 3 a.m. on a Sunday. We should deliberately trigger that fault ourselves during normal business hours. By writing software that randomly kills vital processes and severs network links in live production environments, we force our fault tolerance machinery to be continually exercised. It sounds totally counterintuitive. We're actively breaking the systems we're paid to protect. But it acts like a vaccine. Exposing the system to controlled doses of chaos builds a robust immune system.
We have covered a tremendous amount of ground in this explainer today, peeling back those clean abstractions to look at the messy, chaotic reality under the surface of our digital world. We know now that reliability is not about achieving perfection. It's entirely about building an architecture resilient enough to weather the storm. Entropy is coming for our hardware, dormant bugs are hiding in our software logic, and human error is always just one mistaken keystroke away. The central takeaway here is that the question is no longer if a critical fault will occur, but simply when. So I want to leave you with this final vital thought to consider as you look at the apps and services you rely on. When the inevitable accident finally arrives, is your system truly ready to tolerate it?